Okay, so that's the form of Jeffrey's prior in general. So what is it? It's the square proportional to the square root of minus the expected value of the second differential of the log likelihood function. That's a bit of a mouthful, but you do it very much in steps. And we're going to work through the binomial example. So if we have binomial data, we would say that y comes from a binomial distribution described by n and tau, where tau takes the values over the range 0 to 1. And then we go, right, the first step that we have to do is get the log of this. So this is we get our likelihood function first, which is f of y given tau, and that's equal to just your binomial distribution. So y n choose tau times tau to the y, 1 minus tau to the n minus y. Remember, you'd be given that in your formula sheet. Okay, so what's your next stage? If you're working from in right the way out, next stage is get the log of both sides. So we get the log of our likelihood equals log of n choose y, and unless I state otherwise, I'm a statistician, so I use log to the base e, like any proper scientist would use. We're not engineers here. Plus y log of tau plus n minus y of log of 1 minus tau. Hopefully that should all be fairly easily done. And this is on page 53 of your notes, with some slight typos. So you might want to correct your typos as you're going along. Then the next thing we have to do is differentiate twice with respect to tau. So we'll differentiate with respect to tau once. d tau of log of f of y given tau equals, well, that's going to disappear. It doesn't have a tau term in it. That's going to be 1 over tau, so it's y over tau. And then we have plus n minus y 1 over tau, and then the differential of what's inside it is minus 1. For convenience, you can write that as n tau to the minus 1 minus n minus y 1 minus tau to the minus 1, if that is your own personal preference for helping your differentiation on the next round. Because you have to differentiate it again with respect to tau. So d squared d tau squared of log of f of y given tau is equal to minus y tau squared minus n minus y, and then this is where you have to track all your minuses. You get a minus 2, so you get multiplying this by minus 1, and then a minus 1 in here, so it becomes a plus 1 minus tau squared. Let's zoom in on this a bit just so you can see. There we go. And then the next stage you're asked in this big mechanics thing, so we've done everything inside these round brackets, and we need to get the expected value of that. So the expected value, well, that comes into play through your y. What's the expected value of y from a binomial distribution? Well, it's the number of observations we have times our proportion. So it's n tau. Think about it as tau is y over n. So we replace y's with n taus, and that gets our expected value of this. Expected value of the second differential with respect to tau of log of f of y given tau equals minus n tau over tau squared minus n tau over 1 minus tau to b squared. As you can see, you can do a bit of cancelling here, and we're all for cancelling, which is equal to minus n over tau minus n, and then that becomes 1 minus tau over 1 minus tau to b squared, so over 1 minus tau. What's your next natural thing to do there? Yeah, so it's actually to express this as a complete fraction rather than as a sum of two things. So it becomes minus n, take that out, becomes 1 minus tau, that's plus tau over tau into 1 minus tau, which is equal to minus n, they cancel each other out, over tau 1 minus tau. And then we get minus this. That's the next thing we're asked for. So minus the expected value of d squared d tau squared log of f of y given tau. So that's the log of the log likelihood there, is n over tau to 1 minus tau. I'm going to write that in this form here, just so it fits all on the one line. And then to finish off getting Jeffreys prior, Jeffreys prior is proportional to the square root of that. How would you get the square root of this? Well, it's the square root of n, and then tau to the minus a half, 1 minus tau to the minus a half. So we get the square root of minus expected value d squared d tau squared of the log likelihood equals square root of n, tau to the minus a half, 1 minus tau to the minus a half. Right, we're almost there. What we want to now consider is, we've said that g of tau, which is our Jeffreys prior, is proportional to the square root of n times tau to the minus a half, 1 minus tau to the minus a half. Now recall from what's on the board that a beta AB distribution is equal to gamma of A plus B over gamma of A, gamma of B, and tau to the A minus 1, 1 minus tau to the B minus 1. Okay, you see that? What do you immediately start to match up with one another? Yes, so you get tau to the minus a half, tau A minus 1, and 1 minus tau to the minus half will be going to tau, 1 minus tau to to the b minus 1. So a minus 1 is equal to minus a half. So a equals to a half. B minus 1 equals minus a half. B is equal to a half. And therefore you can define your distribution by just plugging in a half into these formulas here, and you get the g tau equals gamma of a half plus a half is 1 over gamma of a half, gamma of a half, and then tau to the minus a half, 1 minus tau to the minus a half. You could complete this by going that's actually equal to 1, because it's 0 factorial. So you could slightly simplify this by going it's 1 over gamma to the half, gamma to the half, tau to the minus a half, 1 minus tau to the minus a half. And that's how you calculate Jeffrey's prior for a binomial likelihood.